Improved risk management for geothermal systems. Enhanced geothermal systems (EGS) are considered a promising source of energy that is clean, provides a sustainable baseload for heat and electricity, and is an emerging key technology in the long-term transition to a fossil fuel-free future. However, developing a geothermal reservoir requires the forceful creation of fluid pathways in the deep underground by injecting large amounts of water under high pressure. Induced seismicity is an inevitable and well-known, yet poorly understood byproduct of this technology and has caused serious public concern and skepticism, leading to the shutdown of several EGS projects in the past. Managing the induced seismicity risk is therefore crucial for the development and further exploitation of EGS technology towards market-ready power and heat supply in urban environments. In a new study now published in Science Advances, a team of scientists reports on a successful attempt to control induced seismicity during the deepest ever hydraulic stimulation of a geothermal well in Helsinki, Finland. In a collaborative effort by a team of international researchers from commercial companies, academic institutions and universities, a safe stimulation strategy was designed and successfully applied, preventing the occurrence of a project-stopping induced earthquake with a magnitude larger than 2, a limit imposed by local authorities for the safe continuation of the Saint 1 Deep Heat Oil Energy project. The near real-time processing of seismic data retrieved from an ad hoc installed network of borehole and surface geophones provided the critical input for the safe operation of the stimulation, says lead author Grzegorz Kwiatek, a scientist based at GFC Potsdam. In the project, a traffic light-style system involving near real-time seismic monitoring allowed active feedback and guidelines to the stimulation engineers on how to adjust pumping rates and pressure at the injection. Professor Georg Driesen, head of the geomechanics group at GFZ, states, "This feedback in near real time was the key to success and allowed to deepen the understanding of the reservoir seismic response and the hydraulic energy release at depth, while ensuring promptness in the technical response to increased seismic activity." This allowed immediate adjustment of the reservoir treatment through mitigating injection rate and duration of resting periods that were applied in the course of the months-long experiment, and ensured the successful control of maximum observed magnitude of the induced seismic events. While the quantitative results successfully applied here to avoid larger seismic events are not directly transferable to other tectonic settings, the methodology and concept we developed in our study can be useful to other EGS projects to limit the seismic risk and derive ad hoc stimulation strategies, says Grzegorz Kwiatek. The Saint 1 Deep Heat Oil Energy project is now approved for further advancement, and after completion of a second well will move on to implementation of a fully functional geothermal plant for local heat provision. Mapping industrial hum in the U.S. using a dense sensor network that scanned the United States between 2003 and 2014, researchers have identified areas within the country marked by a persistent seismic signal caused by industrial processes. At the 2019 SSA annual meeting, Omar Marcio of Los Alamos National Laboratory said that he and his colleagues are developing a map of this harmonic tonal noise, or industrial hum. The harmonic tonal noise map that Marcio and colleagues are developing can pinpoint where certain types of industrial activity are prominent. Marcio and his colleagues first noted the industrial signals in acoustic data they were collecting from infrasound experiments to study the global propagation of noise from phenomena like ocean storms. They realized that part of the infrasound signal they were detecting was coming from wind farms tens of kilometers away from the detectors. They realized that the wind farms should send a seismic signal through the ground as well, and began searching for these signals in seismic data collected across the U.S. by the Transportable Array, a mobile network of 400 high-quality broadband seismographs that has been moved east to west across the U.S. The characteristic signals are produced by large industrial machinery like the wind farm turbines in places like the Hoover Dam, and large water pumping stations in Washington state and California, Marcio explained. We realized that the same processes that happen in a big wind farm, you would see in big pumps, anything that has rotating parts, hydroturbines or blowers, anything that moves very harmonically and creates these tonal signatures, he said. We are looking at big machines, we are not talking about something like the air conditioner in a house. Marcio said the map could help researchers learn more about where these industrial signals might interfere with other seismic data collection efforts. Scientists building massive and hypersensitive instrumentation such as particle colliders might also benefit from knowing about nearby sources of industrial hum. Marcio noted that many researchers, including himself, have sought to erase instead of enhance these kinds of industrial signals in their work. Some of the techniques we have to study earthquakes, for instance, try to get rid of all these features because they are noise, he said. But one person's noise is another person's signal,